Far out in the dark, the James Webb Space Telescope is staring at the oldest light there is, and what it sees breaks the rules. Galaxies already bright and grown up, only a few 100 million years after the Big Bang. Stars born too fast. A universe that built itself quicker than our best science allows. Tonight we travel to the edge of everything we can see. If cosmic mysteries pull you in, hit like and subscribe. Hold on, we begin. Picture a machine that can look backward through time. We actually built one, and it floats 1 million miles from Earth right now. Its name is the James Webb Space Telescope. People call it Webb for short. It is the most powerful eye humans have ever launched into space, and its main job is strange. It hunts for light that is older than the Earth, older than the Sun, almost as old as the universe itself. Here is the trick that makes it possible. Light is fast, but it needs time to travel. When you look at the moon, you see it as it was a little over 1 second ago. When you look at the Sun, you see 8 minutes into the past. The light left, crossed the gap, and only then reached your eyes. Now, stretch that idea across the whole cosmos. Some galaxies are so far away that their light has been flying toward us for billions of years. When Webb catches that light, it sees those galaxies as they were billions of years ago. The picture is ancient. The galaxy in it might look completely different today, or it might be gone. So, a telescope this powerful becomes a kind of time machine. Look farther, and you look further into the past. Webb was built to look farther than anything before it. To pull this off, engineers gave it a giant golden mirror. It stretches more than 21 feet across, about as tall as a 2-story house. A bigger mirror catches more light, and faint ancient light needs every scrap of help it can get. They also made Webb see in a color our eyes cannot. It watches the sky in infrared, the same kind of light your skin gives off as heat. Old light from the early universe arrives, stretched out and cooled into infrared, so a normal camera would miss it. Webb was built to catch exactly that glow. Then there was the heat problem. Webb's own warmth would blind it, like trying to spot a candle while staring into a campfire. So the telescope carries a sunshield the size of a tennis court, folded up at launch and opened in space. It blocks the sun and keeps the mirror colder than 300 degrees below zero. Only in that deep cold can Webb feel the faint warmth of the first galaxies. And it does not orbit close to us. Webb sits about 1 million miles away, 4 times farther than the moon, parked at a quiet spot where it can stare into the dark without Earth getting in the way. All of this, the giant mirror, the heat vision, the freezing shield, the lonely outpost, points at one goal. Reach back toward the beginning. See the universe, when it was brand new, when scientists finally aimed this machine at the deepest, oldest part of the sky. They expected to confirm a story they already trusted. A calm, simple story about how everything began. The very first images would tear a hole in that story. Before we travel to the edge of the universe, let us be clear about what that edge actually is. There is no wall out there. No fence, no cliff, no giant sign that says the universe ends here. If you flew a spaceship in one direction forever, you would never smack into a boundary. So when scientists talk about the edge, they mean something stranger. The edge is a limit of sight. Space itself keeps going. What runs out is the light that can reach us. Think about standing on a beach at night, looking out at the ocean. You cannot see the whole sea. You can only see as far as the light reaches before the dark swallows it. The water keeps going past that point. You just cannot see it. The edge of your view is set by light. The universe works in a similar way. We can only see as far as light has had time to travel to us since the universe began. Light from beyond that has not reached us yet. That circle of everything we can see has a name. Scientists call it the observable universe. Its outer rim is the edge in our story. Here is what makes that rim special. The farther out you look, the older the light gets. Distance is time. So the very edge of what we can see is also the oldest thing we can see. It is light that left its source soon after the universe was born. How young are we talking? The universe is about 13.5 billion years old. The galaxies at the edge sent out their light when the cosmos was only a few 100 million years old. They are the first generation, the very beginning of structure in the universe. That early time has a name too. Scientists call it cosmic dawn, the stretch when the first stars and the first galaxies were just flickering on. For a long time, nobody could see that far. The light was too faint and too old, stretched and dimmed by its long trip across space. That is exactly the gap Webb was built to close. Its giant cold mirror and its heat vision were designed to grab that faint, ancient glow from the edge, to pull cosmic dawn out of the dark and finally show it to us in detail. And scientists were desperate to see it. They had a theory about what cosmic dawn should look like, a clear, careful story built over many years about how the first galaxies were born and grew. They were sure of it. They just needed a machine sharp enough to check the early pages of that story. So picture what they expected as Webb turned toward the edge. A quiet, simple beginning. Small specks of light, barely formed, just starting to glow. What Webb actually pulled out of the dark looked nothing like that quiet beginning, and the first clue was hiding in a single deep photo of the sky. That single deep photo was full of faint smudges of light. To understand why some of them shocked scientists, you need to know the one measurement that rules this whole hunt. It is called redshift. Redshift sounds technical. The idea behind it is simple, and you can hear it in everyday life. Think about a fast car racing past you with its engine roaring. As it comes toward you, the sound is higher and tighter. As it speeds away, the sound drops lower and stretches out. The car never changed its engine. The sound waves got squeezed coming at you and stretched going away. Light does almost the same thing. Light travels in waves too. When the thing giving off light is rushing away from us, its light waves get stretched. Stretched light slides toward the red end of the rainbow. So scientists named this stretch redshift, because the light shifts toward red. Now add the biggest fact in all of space science. The universe is expanding. Everything is slowly spreading apart, like raisins in a loaf of bread dough rising in the oven. As the dough puffs up, every raisin drifts away from every other raisin. Galaxies are the raisins. Space itself is the dough. As space grows, it stretches the light traveling through it. The longer that light has been flying, the more space has stretched underneath it, and the more its waves get pulled toward red. This gives scientists a powerful tool. Measure how much a galaxy's light has been stretched, and you learn how far that light has traveled. A small stretch means the galaxy is fairly close and its light is fairly young. A huge stretch means the galaxy is far away and its light is ancient. So redshift is really a clock and a ruler at the same time. A high redshift tells you the light crossed a vast distance. It also tells you the light left long ago, near the beginning of the universe. This is why Webb headlines always come with a redshift number stapled to them. When you hear that a galaxy sits at a redshift above 10, your alarm should go off. That galaxy sits deep inside cosmic dawn. You are staring at light from the universe's first few 100 million years. And there is a catch that makes Webb essential. When light gets stretched far enough, it leaves the rainbow our eyes can see. It slides past red into infrared, the heat light we talked about. A regular telescope goes blind to it. Only an infrared eye like Webb can still catch it. So, redshift is the score that tells scientists how deep into the past they are looking. The higher the number, the closer to the beginning. The closer to the beginning, the more the rules of the early universe are supposed to hold true. For years, the highest redshifts stayed just out of reach. Scientists could guess what waited at cosmic dawn, but they could not measure it cleanly. Webb changed that overnight. It started pulling galaxies out of the dark with redshifts higher than anyone had ever confirmed. And the moment those numbers came back, a worry crept in, because the galaxies attached to them were doing something they were never supposed to do. In the summer of the year 2022, scientists finally aimed Webb at the deep sky and took its first long exposure. What came back changed the mood in every astronomy lab on Earth. The image looked simple at first, a black square sprinkled with glowing dots, like dust caught in a sunbeam. But every one of those dots was a galaxy, thousands of them, packed into one frame. Here is the part that bends your mind. That whole crowded photo covered a patch of sky smaller than a grain of sand held at arm's length. Pick any tiny, empty-looking spot above you, cover it with one grain of sand, and Webb found thousands of galaxies hiding behind it. The universe is that full. Scientists call a picture like this a deep field. The idea is to point the telescope at one small, dark patch and leave the shutter open for a long time. Light trickles in, hour after hour. Faint things that a quick photo would miss slowly build up, dot by dot, until the dark patch blooms with galaxies. The closer galaxies showed up as clear spirals and bright blobs, but scientists were hunting something else. They wanted the faint red specks scattered in the background, the ones so dim they almost vanished into the black. Those red specks were the prize. Red meant stretched light. Stretched light meant huge distance and ancient age. Webb even got help from gravity itself. Sitting in the middle of that first image was a heavy cluster of galaxies. Its gravity is so strong that it bends space around it, like a thick lens made of glass. Light from even more distant galaxies passes through that lens and gets magnified on its way to us. Nature handed Webb a free zoom, letting it peek at things hiding even farther back. So the team started picking out the reddest, faintest dots and asking the key question, how far, how old? They ran the light through their instruments and measured the stretch. The redshift numbers started climbing, 10, 11, 12. Each step backward in time, deeper toward cosmic dawn than anyone had ever clearly reached. That alone was a triumph. Webb was working. It was seeing farther than any telescope in history, exactly as promised. The faint red specks were real galaxies from the dawn of everything. Then the team measured how bright those specks were, and a quiet unease spread through the room. To understand why a little extra brightness made trained scientists nervous, you first have to know the story they walked in believing. The careful, step-by-step story of how the early universe was supposed to grow. For more than 50 years, scientists built a careful story of how the universe grew up. They tested it, checked it, and trusted it. It went something like this. In the beginning, right after the Big Bang, the universe was almost perfectly smooth. Just a hot fog of the two simplest gases, hydrogen and helium, spread out everywhere. No stars, no galaxies, only a fading glow from the birth of everything. The cosmos was a dark, quiet soup, but the soup was not perfectly even. Some spots held a tiny bit more gas than others. Those slightly heavier spots had slightly stronger gravity, and gravity is patient. Over millions of years, it pulled gas inward, piling more and more into those dense pockets. Eventually, a pocket grew heavy enough to collapse and catch fire. The first star switched on, then more followed. Small clumps of stars gathered into the first little galaxies, faint and small and rough around the edges. Here is the key word in the old story. Slow. Everything was supposed to take its time. Small galaxies were meant to drift together and crash, slowly merging into bigger ones. Picture small streams flowing together to build a river, then rivers joining to build a sea. Galaxies were supposed to grow the same way, piece by piece, over hundreds of millions and even billions of years. The big, grand galaxies like our own Milky Way were the final result, built up near the end of a long, slow climb. The chemistry followed the same slow clock. The early universe held only those two light gases. Every heavier thing, the carbon in your body, the oxygen you breathe, the iron in your blood, had to be cooked inside stars and then blasted out when those stars died. That takes many generations of stars living and dying, so the early universe was supposed to be chemically plain, almost no heavy elements, just simple gas and a few young stars. Put it all together and you get a clear picture of cosmic dawn, a slow sunrise, The first few 100 million years should hold only small, dim, simple galaxies. Tiny building blocks, just getting started. Faint sparks barely strong enough to see, made of plain gas, with hardly any heavy elements at all. Scientists were so confident in this picture that they used it to predict what Webb would find. They expected the telescope to reach back to cosmic dawn and show them a nursery full of baby galaxies. Small, faint, simple, right on schedule. This was a careful prediction, not a wild guess. It came from decades of math, observations, and computer models that matched the universe we see around us today remarkably well. The old story worked beautifully for almost everything closer to home. So, when Webb aimed at the edge, the team felt ready. They thought they knew the ending before they read the page. Confirm the slow sunrise, fill in some fine detail, collect the prize. The universe had other plans. The galaxy's Webb, pulled from cosmic dawn, broke every part of that picture. They were big, they were bright, and the first sign that the careful old story was in trouble came down to one stubborn problem. These ancient galaxies were shining far too brightly. A bright galaxy is a busy galaxy. That simple fact is what made scientists nervous. When astronomers see a galaxy pouring out light, the easiest explanation is stars. Lots of stars, especially big, hot, blazing stars that shine like searchlights. To gather that many stars, a galaxy normally needs time. It has to pull in gas, form star after star, and slowly stack up enough of them to glow that brightly. So brightness is a rough measure of how grown up a galaxy is. More light usually means more stars, and more stars usually means more time has passed. A blazing galaxy is supposed to be an older galaxy. Now remember where Webb was looking. At cosmic dawn, at galaxies from the first few 100 million years after the Big Bang. The universe was a newborn. There had not been enough time to build big, bright, star-packed galaxies. The old story said these places should be faint little sparks, just flickering on. Instead, Webb found some of them blazing. A few of these early galaxies were shining with the strength of billions of suns, far more light than a half-built baby galaxy should ever manage. It was like opening the door to a kindergarten and finding a few of the kids already 6 feet tall. The age does not match the size. Something is off. Scientists faced two uncomfortable choices, and both shook the old story. Maybe these galaxies really were packed with stars. If so, the early universe built huge piles of stars at lightning speed, far faster than any model allowed. The slow sunrise would have to become a sudden blast of fire, or maybe the brightness came from something other than ordinary stars. Maybe a hidden monster was feeding in the center of each galaxy, throwing off light as it ate. That idea has its own problems, and we will get to those creatures soon. Either way, the easy version of cosmic dawn was in trouble. A quiet nursery does not glow like a city at night, and the scale of the surprise mattered. This was one galaxy at first, then another, then many. Webb kept finding bright early galaxies, again and again, in patch after patch of sky. One oddball you ignore, a crowd of them you cannot. The team checked their work over and over. They worried about mistakes. A galaxy can fool you. Its light can get boosted. Its distance can be misjudged. Its size can be guessed wrong. They knew all of this. So they treated the first bright galaxies with suspicion, the way a careful detective doubts a story that sounds too clean. But the brightness would not go away. The more they looked, the more these glowing early galaxies piled up. And then a specific group of them stepped into the spotlight. A small set of galaxies so bright, so heavy, and so early that one nervous nickname spread through the whole field almost overnight. People started calling them the universe breakers. In early 2023, a team of scientists published a result that made headlines around the world. They had found 6 galaxies in Webb's data that should not have been possible. These 6 sat at a time roughly 500 to 700 million years after the Big Bang. Young by cosmic standards, the universe had lived only a small slice of its life, and yet these galaxies looked enormous. How enormous? Some of them appeared to hold as many stars as the entire Milky Way, our own giant home galaxy. The Milky Way is a spiral wheel of a few 100 billion stars. It took most of the history of the universe to build it, more than 13 billion years of slow growth. But these 6 galaxies seem to have grown a Milky Way's worth of stars in a few 100 million years. That is like watching a baby grow into a full-sized adult in the first week of life. The timeline simply does not allow it. The nickname wrote itself. People called them universe breakers because their very existence seemed to break the rules of how galaxies are supposed to grow. Step back and feel the weight of that. The old story said the early universe should hold only tiny building blocks, small clumps, slowly gathering. These 6 galaxies looked like finished products sitting at the very start of the story, like finding skyscrapers in a photo of an empty construction site. The scientist who led the work admitted the obvious. The result was so strange that even the team struggled to believe it at first. They expected to find baby galaxies. They found apparent giants. One of them later described the feeling as staring at something that broke their understanding of the cosmos. News outlets ran wild with it. Headlines shouted that the James Webb Space Telescope had broken the universe, or broken science, or broken the Big Bang. The phrase, universe breakers, stuck to these galaxies and never let go. Now, the careful part. The team was honest about the uncertainty. These were early measurements. The scientists read the galaxy's colors to estimate their mass, a quick method that leaves real room for error. The masses were estimates. The distances were strong guesses. There was room for the numbers to shift once better data came in. In fact, some scientists suspected the masses might shrink with closer study. Maybe a few of these galaxies were lighter than they first looked. Maybe their brightness was being faked or boosted by some trick of physics. That hope, that the universe breakers might calm back down to normal, became its own quiet question hanging over the field. So the 6 universe breakers split scientists into 2 camps. One camp said, "Wait, these numbers will settle once we measure them properly." The other camp said Webb keeps showing us early galaxies that are too big and too bright, and a few corrections will not erase the pattern. Both camps agreed on one thing: these galaxies needed to be measured the right way, with the gold standard tool that can pin down exactly how far and what kind a galaxy really is. But even if the numbers shrank a little, one hard problem refused to budge. Building a galaxy that heavy, that fast, runs straight into a wall that physics itself seems to put up. To see why a heavy early galaxy is such a headache, you have to understand how a galaxy gains weight in the first place. A galaxy's mass is mostly its stars. To get heavy, a galaxy must build stars, and to build stars, it needs raw material. That material is gas, mostly hydrogen, the same simple stuff that filled the early universe. Gravity pulls the gas into dense knots. The knots heat up and ignite, and new stars are born. But there is a speed limit on this. Gas does not collapse into stars instantly. It has to cool down, fall inward, and gather. Newborn stars also push back. The biggest, hottest stars blast out fierce winds and explode as they die, shoving nearby gas away and blowing it right out of the galaxy. That blowback slows down the next round of star birth. A galaxy partly chokes off its own growth. Because of this push and pull, scientists believed galaxies could only build stars so fast. There was a rough ceiling on how much mass a galaxy could pack on in a given stretch of time. Think of it like filling a bathtub while the drain sits half open. You can pour fast, but some water always escapes. So the tub fills at a limited pace. The universe breakers seem to ignore that ceiling completely. To grow as heavy as the Milky Way in only a few 100 million years, these galaxies would have needed to turn gas into stars at a furious rate, far above the speed scientists thought was even possible. The bathtub would have to fill almost instantly, drain and all, Run the numbers, and it gets worse. To build that many stars that fast, some of these early galaxies would have needed to convert nearly all of their gas straight into stars, with almost nothing wasted. In the nearby universe, galaxies are sloppy. They turn only a small share of their gas into stars and lose the rest. For these early galaxies to work, they would have to be almost perfectly efficient, squeezing out stars with a precision no galaxy today comes close to matching. That is the deep problem. The brightness was a clue, but the mass was the real shock. A bright galaxy might be explained away. A galaxy as heavy as the Milky Way, sitting at the dawn of time, is far harder to wave off. It would mean one of a few strange things is true. Maybe gas collapsed into stars far faster in the early universe than it does now. Maybe the first galaxies grabbed and held their gas instead of blowing it away. Maybe the very first stars formed in a way we still do not understand, building mass at a blistering pace. Every one of those answers rewrites a piece of the old story. Every one of them speeds up cosmic dawn from a slow sunrise into a fast, fierce ignition. Scientists knew the stakes. If even a few universe breakers held up under careful study, the textbooks would need new chapters. So everything came down to checking the measurements. The early masses came from color, which meant they came with doubt. To clear that doubt, scientists needed to read a galaxy's light in detail. And one of the first ancient galaxies they locked down was a faint red smudge so small you could blink and miss it. Yet, that little smudge would set a record that stood as the edge of the known universe. The galaxy had a clunky catalog name, the kind only a scientist could love. Most people would never remember it, so let us just call it the little red smudge, because that is exactly what it looked like. In Webb's images, it showed up as a single dim red dot, easy to miss among thousands of brighter neighbors. It looked like a faint speck of red light, with none of the spiral arms or glowing disk you see in grown-up galaxies, just a smudge. But that little smudge was special. When scientists measured how much its light had been stretched, the number came back enormous. Its redshift was above 13, one of the highest ever measured. That stretch meant its light had been traveling for an almost unimaginable time. When astronomers worked out the age, they got a stunning answer. They were seeing this galaxy as it looked only about 325 million years after the Big Bang. The universe has been around for more than 13 billion years. This galaxy's light comes from the first few 100 million of them, almost as far back as anyone had ever seen. For a while, this faint red dot held a title. It was the most distant galaxy humanity had ever confirmed, the current edge of the known universe, a real, measured object from the deep dawn of time, sitting right at the limit of what Webb could reach. And here is what made even this tiny smudge a little unsettling. It already showed signs of being a real, organized galaxy, with a surprising amount of starlight packed into a small space. Even at the dawn of time, this thing was already doing the work of being a galaxy. For scientists, the little red smudge was both a triumph and a warning. The triumph was obvious. Webb had reached deeper into the past than any machine before it, and brought back a confirmed galaxy from the earliest era ever seen. The telescope was doing exactly what it was built to do, and doing it better than anyone dared hope. The warning was quieter. Even here, this close to the beginning, the universe was already glowing with starlight. The dawn of cosmic time was already busy making galaxies. And if a real galaxy already shone at 325 million years, what was happening even earlier, in the dark just before it? That question would drive Webb to push farther and farther back, hunting for galaxies even closer to the very first moment. Each new record would be harder to win, and each one would raise the same uneasy feeling. But there was a trap waiting in all this excitement. A distant galaxy is slippery. A faint red dot can lie about how far away it is. The early universe breakers had taught everyone a hard lesson about trusting a quick look. So before scientists could believe any of these record-breaking galaxies, before they could say a single one truly came from the dawn of time, They had to rule out the ways a galaxy can fool even the sharpest telescope in history. And there are more of those ways than you might think. Good scientists are professional doubters. The bigger the claim, the harder they try to knock it down. And a galaxy from the dawn of time is about as big a claim as you can make. So before anyone celebrated, the doubters went to work. Their first worry was distance itself. The early measurements came from a quick method. Scientists looked at a galaxy's colors across a few filters and used those colors to estimate how stretched the light was. It is fast and useful, and it can stumble. Here is the danger. A galaxy sitting fairly close to us, full of dust, can glow a deep red. A galaxy at the dawn of time, with its light stretched, also glows a deep red. Through a small set of filters, those two very different galaxies can look almost like twins. One is near and dusty. One is ancient and far. Mix them up, and you might crown a nearby dust bucket as a record-breaking galaxy from cosmic dawn. That kind of mistake has burned astronomers before, so they treated every early redshift as a suspect until proven otherwise. The second worry was brightness, and this one is sneaky. A galaxy's light comes from more than its stars. Glowing gas around young stars can fire off intense beams at specific colors, called emission lines. If one of those bright lines lands in the wrong filter, it can make a modest galaxy look far brighter and heavier than it really is. The galaxy seems packed with stars, when really a burst of glowing gas is faking the signal. That single trick could shrink some universe breakers down to size. A galaxy that looked as heavy as the Milky Way might turn out to be much lighter once scientists subtracted the glow of its gas. The brightness was real. The story behind it was uncertain. There was a third worry, and it is the strangest of all. The light might not be coming from stars at all. It might be coming from a feeding monster. In the heart of many galaxies sits a giant black hole. When gas spirals into one, it heats up and blazes with the strength of a whole galaxy before it falls in. From far away, that blaze can be mistaken for the light of billions of stars. So a galaxy that looks big and mature might really be a smaller galaxy with a hungry black hole at its core, throwing off light as it eats. We will return to those monsters later, because they cause trouble of their own. Add it all up, and you can see why scientists held back. A faint red dot from the early universe might be exactly what it seems. Or it might be a nearby dusty galaxy in disguise, or a small galaxy running a glowing gas trick, or a black hole wearing a galaxy's clothes. 4 very different stories, all hiding behind the same little smudge of red light. This is why the universe breakers, for all their headlines, started as a question. The honest answer in those first months was simple. We are not sure yet. To turn the maybe into a yes, scientists needed a far more powerful test, a way to read a galaxy's light so precisely that all the disguises fall away, leaving only the truth about its distance and its nature. That test exists. And when they finally used it on these ancient galaxies, the disguises did fall, one by one. The tool that cuts through every disguise is called spectroscopy. The word sounds heavy. The idea is beautiful and simple. Start with a rainbow. When sunlight passes through a prism or through raindrops, it spreads into a band of colors. Spectroscopy does the same thing to a galaxy's light. It takes that faint smudge and spreads its light out into a full spectrum, every color laid side by side. And inside that spread of color, nature hides a fingerprint. Every kind of atom, hydrogen, helium, carbon, oxygen, deals with light in its own exact way. Each one soaks up or gives off light at very specific colors, and no other element copies the pattern. Hydrogen leaves one set of marks. Oxygen leaves another. When you spread a galaxy's light into its full spectrum, those marks show up as sharp lines at fixed spots in the rainbow. Those lines are a fingerprint. Read them, and you learn what the galaxy is made of. You can tell which elements are present, which tells you whether a galaxy is simple and young or already rich with heavier stuff. But the fingerprint does something even more powerful. it nails down distance. Scientists know exactly where each element's lines should sit when the gas is standing still. In a faraway galaxy, those lines are shoved toward the red end of the spectrum, stretched by the expanding universe. By measuring how far the whole fingerprint has slid, scientists read the redshift with stunning precision, an exact number locked in by the laws of physics. This is the difference between a hunch and a verdict. The quick color method says a galaxy is probably far away. Spectroscopy says this galaxy sits at this exact distance, no argument. It is the gold standard, the measurement that turns a candidate into a confirmed fact. It also exposes the imposters. Remember the nearby dusty galaxy that can fake a high redshift? Under spectroscopy, its fingerprint sits in the wrong place, and the disguise falls apart. Remember the feeding black hole that can fake a galaxy's brightness? Its light leaves its own telltale marks, broad and wild, far different from the calm glow of ordinary stars. Spectroscopy can tell the two apart. There is one catch. Spreading a faint galaxy's light into a full spectrum takes a lot of light, and these early galaxies are dim. Webb sometimes has to stare at a single target for many hours, even tens of hours, gathering every scrap of light before the fingerprint becomes clear. It is slow, patient, expensive work. You cannot do it for every dot in the sky. So scientists save it for the most important targets, the galaxies that could rewrite the story. That is exactly what they did with the strangest early galaxies. They pointed Webb at them and held the gaze, hour after hour, letting the ancient light pour in until each fingerprint sharpened into focus. And when those fingerprints finally appeared, they settled the biggest question hanging over the whole field. These ancient galaxies truly were as distant and as early as everyone feared. The strange ones were real. The disguises were gone. What remained was a pattern, growing galaxy by galaxy, that scientists could no longer explain away. For the first year, the strange early galaxies lived in a soft, uncertain space. They were candidates, maybes, exciting headlines with a question mark stamped on them. A careful scientist could still hope the whole thing would shrink away once the real measurements came in. Spectroscopy ended that comfort. One by one, Webb locked down the fingerprints of these ancient galaxies. The distances stopped being guesses and became facts. Galaxy after galaxy was confirmed sitting in the first few 100 million years of the universe, exactly where it had no business being so bright or so grown, and that flipped the whole problem on its head. At first, the burden of proof sat on the scientists making the wild claims. They had to convince everyone that these galaxies were real and truly ancient. The doubters could fold their arms and say, "Prove it." After enough confirmations, the burden flipped. Now the doubters had the hard job. The strange galaxies were proven. The pattern was measured. Anyone who wanted to keep the old, slow story of cosmic dawn had to explain away a growing pile of confirmed early galaxies, each one stamped with a gold standard distance. It became like a trial where the evidence keeps stacking higher on one side of the room. One weird galaxy is an anomaly you can shelve and forget. A handful might be a fluke, but Webb kept finding them and kept confirming them in field after field of sky. The early universe was throwing bright, well-built galaxies at the telescope faster than the old models could absorb. Some of the first wild numbers did calm down, exactly as the cautious camp predicted. A few galaxies that looked as heavy as the Milky Way turned out lighter once scientists measured them properly. Part of their glow came from gastrix or feeding black holes, just as feared. The cautious scientists were right to push back. But here is the twist that mattered. Trimming the numbers did not fix the problem. Even after the corrections, even with the masses brought down to Earth, far too many galaxies were still too bright, too built up, and too early. Shaving the extremes only made the pattern harder to deny, because now it rested on solid measurements rather than hopeful guesses. Scientists put it simply. Webb sharpened the problem. The early galaxies had grown from a shaky rumor into a confirmed feature of the real cosmos, written in carefully read light. The story of cosmic dawn had officially cracked. The slow sunrise was struggling to survive. Something made the early universe build galaxies faster, brighter, and more completely than anyone had planned for. And just when scientists were starting to absorb all of this, Webb did what Webb does best. It reached even deeper. It pushed past every record it had already set and locked onto a galaxy from a time so early that it made the universe breakers look almost ordinary. This new galaxy would become the most distant object humanity has ever confirmed, and everything strange about cosmic dawn would show up inside it, sharper than ever. In January of the year 2026, scientists announced a new champion. They had confirmed the most distant galaxy ever seen, and it shattered the old record. Its name is MOME, Z14. After that, let us mostly call it the record holder, because the name barely matters next to what it means. This galaxy sits at a redshift of more than 14, the highest anyone has ever confirmed. Its light has been stretched so far that it presses against the very limit of what Webb can detect. To even find it, the telescope had to reach deeper into the past than it ever had before. The record holder was a real, working galaxy. A bright one, already switched on, lit up, and flooding the young cosmos with light. It was a true galaxy, alive and shining, at a moment when the universe had barely begun. Just reaching this far back was a historic win. Webb had touched closer to the birth of the cosmos than any instrument in history. On distance alone, this was a triumph for the ages. Distance was only the start of the story. When scientists studied the record holder closely, they found three things that did not fit, all crammed into one tiny galaxy. It was too bright, it was too compact, and it was too chemically rich for its age. Each of those alone would raise an eyebrow. Stacked together, in a galaxy this early, they spell out the entire crisis of cosmic dawn in a single object. Too bright meant it overflowed with light, the same problem the universe breakers raised, now pushed even further back in time. Too compact meant all that light was packed into a tiny space, a whole galaxy squeezed into a fierce, dense knot smaller than scientists expected. And too chemically rich meant it already carried heavier elements, the kind that take many star lifetimes to build, somehow present far too soon. NASA, the space agency that runs Webb, summed it up plainly. The record holder is brighter, smaller, and more chemically enriched than scientists expected for such an early time. That one sentence holds the whole problem of the early universe, confirmed at the farthest edge we can reach. And the measurement here is the gold standard. Scientists locked this galaxy down with careful spectroscopy, reading its fingerprint in detail. The strangeness is checked. The strangeness is real. The pattern Webb had been building, galaxy by galaxy, now reached its sharpest point inside the most distant object we have ever found. The farther the telescope looked, the stranger the early universe became. To feel why this galaxy unsettles scientists so deeply, you have to understand the exact moment it comes from, a time so close to the beginning that, by every rule we trusted, a bright and finished galaxy simply should not be there. Let us go to that moment. 280 million years after the Big Bang. 280 million years sounds like a long time. For a human, it is unthinkable. For the universe, it is the blink right after birth. Let us put it in scale. Take the full life of the cosmos, more than 13 billion years, and shrink it down to a single calendar year. On that scale, the Big Bang happens in the first second of January 1st. Right now, today, is the last moment of December 31st. Every star you have ever seen, every planet, every living thing, all of human history, fits inside that one squeezed year. So where does the record holder fall on that calendar? Its light left around January 7th. The universe was barely a week old in cosmic terms. The decorations from the birth of everything had hardly been cleared away. Now think about what the universe was actually like back then. It was young, dark, and mostly empty of structure. The first stars had only recently begun to flicker on. There had been very little time for anything to grow, to gather, to organize. The cosmos was still close to the smooth, simple fog it started as. In that setting, the old story is crystal clear about what should exist. Tiny clumps, faint sparks, loose gatherings of the first stars, just barely holding together by gravity. Rough little baby galaxies, dim and small and chemically plain, only rough beginnings, the construction site with just the first few beams in place. A bright, compact, chemically rich galaxy does not belong on January 7th. It belongs months later in cosmic time, after generations of stars have lived and died, after gas has gathered and settled, after the slow work of building has had time to run. Finding one this early is like opening a history book to its very first page and seeing a finished city, complete with roads and lights, where the page should show an empty field. That mismatch is the heart of the whole problem. The universe simply had not lived long enough to build what Webb is finding, and the record holder does not stand alone on that early calendar. Other confirmed galaxies sit near it in time, each one a little too bright, a little too grown for the moment it comes from. Webb keeps reaching into the first stretch of cosmic history and pulling out galaxies that look like they skipped ahead, as if they had a head start no one can explain. This is why scientists keep using the same uneasy phrase: too much, too soon. The galaxies are real. The distances are confirmed. The early universe was busy and bright at a moment when it should still have been dim and quiet. So the question grows sharper with every new record. What let the cosmos build finished-looking galaxies in its first few 100 million years, when every rule we trusted says it should have taken far longer? Before we chase that answer, it is worth pausing on something almost unbelievable about how we see these galaxies at all. The light in that photo is not a live feed. It is a message in a bottle, sealed more than 13 billion years ago, only now washing up on our shore. The light Webb caught from the record holder began its journey more than 13 billion years ago. To picture what that means, slow the whole thing down. A tiny piece of light, a particle scientists call a photon, leaves that ancient galaxy. At that moment, there is no Earth, no Sunday, no Milky Way as we know it. The galaxy fires the photon off into the dark, and the photon starts to fly. It flies at the fastest speed there is, the speed of light, almost 6 trillion miles every single year. Nothing in the universe moves faster, and yet it has so far to go that it travels for more than 13 billion years without stopping. Year after year, age after age, that single photon keeps crossing the dark. While it flies, the universe changes around it. Stars are born and die. The first galaxies grow and merge. Our own sun forms, with the Earth circling it. Life appears on that Earth, crawls out of the sea, and slowly builds cities that ask questions about the sky. Dinosaurs come and go, humans rise, all of it happens, while that one photon is still in flight, still crossing the gap, and space itself is stretching the whole time. Remember the rising bread dough. As the photon travels, the universe keeps expanding underneath it, pulling its wave longer and longer. The light that started as a normal glow gets stretched out into infrared, the heat light only Webb can see. The photon arrives tired, stretched, and faint, carrying the fingerprint of a galaxy from the dawn of time. Then, after 13 billion years of flight, it lands on Webb's golden mirror, a single ancient photon, finally caught. Here is the strange truth that comes with all of this. The galaxy on the screen is a ghost. We see it as it was when that light left, more than 13 billion years ago, a snapshot of the deep past. In fact, that galaxy almost certainly does not look like that anymore. Over 13 billion years, it has grown, merged, changed, maybe been torn apart and rebuilt into something else entirely. The version we study tonight has not existed for billions of years. We are looking at a photograph the universe took of itself long before there was anyone to look. That is the secret power of a telescope like Webb. It sees backward in time, Every distant galaxy in its images is a different page from the universe's past, frozen in old light. The farther out Webb looks, the deeper into history it reads. So when Webb stares at the record holder, it is reading the very first pages of the cosmic story, written in light that set off before the Earth was even a thought. We get to hold that ancient message in our hands and study it, line by line. And one line on that page refuses to make sense. When scientists read the fingerprint in that ancient light, they found the marks of heavy elements: carbon, oxygen, the building blocks of planets and people. Elements that take generations of stars to create, somehow already present when the universe was only a week old on our calendar. How did the dawn of time get its hands on the stuff of life so early? Chemistry is a clock. That single idea is why the heavy elements in these early galaxies frighten scientists so much. Go back to the beginning. When the universe was born, it cooked up only the two lightest, simplest gases: hydrogen, the most basic element there is, and a good amount of helium. That was almost the entire shopping list. The early cosmos was a place of plain, light gas and nothing heavier. Everything else, every heavier element, had to be built later, inside stars. A star is a furnace. Deep in its core, it crushes light atoms together to make heavier ones. Hydrogen becomes helium. Helium becomes carbon. Carbon becomes oxygen. And on up the ladder. The carbon in a pencil, the oxygen in the air, the iron in a nail, all of it was forged inside a star. But the furnace only shares its work when the star dies. A big star burns fast, then explodes, blasting its newly made elements out into space. That enriched gas drifts, mixes with fresh hydrogen, and eventually forms the next generation of stars and planets. We are made of that recycled stardust ourselves. Here is the catch, and it is everything. This process takes time. A star has to be born, live out its life, and die before it can spill its heavy elements. Then those elements have to spread and gather into new stars. One full turn of this cycle can take millions of years. To build up a real supply of heavy elements, you need many turns, many generations of stars, living and dying, one after another. So, the amount of heavy stuff in a galaxy works like a clock. A galaxy with almost none is young. Its stars have not had time to cook and spread much. A galaxy rich in heavy elements is old, with many generations of stars behind it. Read the chemistry, and you read the galaxy's age. Now, point that clock at the record holder. It comes from only 280 million years after the Big Bang. On the old timeline, that is barely enough time for the very first stars to be born and start to shine. There should have been almost no chance for many generations to live and die. The galaxy should be chemically plain, made of close to pure early gas. Yet NASA reports that this galaxy already looks chemically enriched. Its light carries the marks of heavier elements, the signs of stellar furnaces that have already burned, exploded, and seeded their surroundings. The clock is reading a much older galaxy than the calendar allows. That is a deep contradiction. It is like meeting a 1-week-old baby that already has a mouth full of adult teeth. The age and the development do not match. Something made this galaxy race through its early life at a furious, compressed pace, and the same hint keeps turning up in other ancient galaxies. Webb keeps finding traces of carbon, oxygen, and even dust in places that should be far too young to have any. The chemistry, like the brightness and the mass, screams the same message. The early universe grew up too fast, so the clue points somewhere specific and strange. If heavy elements are already here this early, then the very first stars must have lived and died sooner than anyone planned, which raises a haunting question about those first stars. What were they like, and how did they burn through their lives so fast? The very first stars were monsters. To understand how the early universe got rich so fast, you have to meet them. These stars were born from the plain early gas, pure hydrogen and helium with nothing heavier mixed in. That simple recipe changed everything about them. In galaxies today, A cloud of gas holds traces of heavier elements that help it cool down, break apart, and form many small stars. Like our Sunday, the early gas had none of that help. It struggled to cool, so instead of splitting into many small stars, it collapsed into a few enormous ones. How enormous? Scientists believe the first stars could be dozens or even hundreds of times the mass of our Sunday. Giant balls of glowing gas, far bigger and far hotter than almost any star we see today. Blazing blue-white, pouring fierce light and radiation into the young dark. And here is the rule that decides a star's life. The bigger the star, the faster it burns. A giant star is greedy. It races through its fuel at a reckless pace and burns out quickly. Our own sun will live for about 10 billion years, calm and steady. These early giants might have lived only a few million years before running dry. In cosmic terms, they flared up and died almost instantly. When one of these giants ran out of fuel, it tore itself apart in a colossal explosion, one of the most violent events the universe can produce. In that blast, the furnace dumped all its freshly made heavy elements straight into space. Carbon, oxygen, and more, flung outward in a single fiery moment. Now you can see how the early universe got rich so quickly. If the first stars were giants, and giants live fast and die young, then the very first generation could have been born, burned, and exploded in just a few million years. That is a heartbeat in cosmic time. One round of monster stars could have seeded the young cosmos with heavy elements almost as soon as it began. Picture it. The first giants ignite across a young galaxy. They blaze for a few million years. Then, one after another, they detonate, spraying carbon and oxygen into the gas around them. From that enriched gas, new stars form, faster and richer than before. The galaxy lights up, fills with heavier elements, and grows bright and dense at a pace the old, slow story never imagined. That single idea could tie the whole mystery together. Fast giant stars would explain the early brightness, since giant stars shine like searchlights. They would explain the early chemistry, since their explosions seed heavy elements right away. And they would explain why these galaxies look so grown up so soon, because everything about them ran on a compressed, violent schedule. There is one humbling catch. Scientists have not yet caught a clear, direct look at one of these first stars. They are worked out from theory and from the clues these early galaxies leave behind. They remain one of the great hunts in astronomy, a prediction still waiting for solid proof. But the fingerprints in Webb's data keep pointing the same way. The dawn of the universe was a place of giants and explosions, burning hot and fast. Those first blazing stars did something else, too, something that should have made the early universe almost impossible to see at all. They lit their fires inside a thick fog that filled all of space, and the way Webb peered straight through that fog is a mystery on its own. Here are chapters 18 through 33, closing out the script. Same rules throughout, with each one handing off to the next, and chapter 33 landing the finale. There was a time when the universe was blind. You could not see across it, even with the sharpest eyes in existence. A thick fog filled all of space, and it swallowed light whole. To understand it, go back to the early cosmos again. After the Big Bang, the universe cooled into a vast sea of hydrogen gas. This gas was neutral, which is a science word for calm and uncharged. Calm hydrogen has a nasty habit. It grabs certain kinds of light and holds onto them. Light tries to cross the gas, gets absorbed, and never makes it through. So, the young universe was foggy. Picture a morning so thick with mist that you cannot see a friend standing a few feet away. Now stretch that fog across the entire cosmos. Any light trying to travel through it got caught and scattered. Scientists call this stretch the cosmic dark ages, because the universe was full of gas, yet impossible to see through. Then the first stars switched on inside that fog, and they started to fight it. A blazing star pours out fierce ultraviolet light, a high-energy kind of light. When that light hits the calm hydrogen fog, it rips the gas apart, tearing electrons off the atoms. Scientists call this ionizing the gas. And here is the key. Once the hydrogen gets torn apart this way, it stops grabbing light. The fog turns clear. Light can finally fly through. So as the first stars and galaxies lit up, they slowly burned away the fog around them. The universe went from a thick grey mist to a clear, see-through cosmos. This great clearing has a name. Scientists call it reionization, the age when the lights came on and the fog lifted. For our story, the timing of that clearing is everything. In the old, careful version, the fog should have hung around for a good while. It should have stayed thick through the first few 100 million years, only clearing slowly as more and more stars joined the fight. That means light from the earliest galaxies should be hard to catch, because it had to claw its way through fog that was still mostly intact. Certain kinds of light should have been almost completely blocked. One in particular, a specific glow given off by hydrogen near young stars, should have been swallowed by the surrounding fog before it could ever reach us. Finding that glow from a very early galaxy should have been close to impossible. The fog should have eaten it. So, scientists had a clean expectation. Look at the earliest galaxies, and certain bright signals should be missing, blocked by the grey sea of gas all around them. The fog was the universe's curtain, and it was supposed to stay drawn for a long time. Then Webb looked at one early galaxy and saw exactly the signal that the fog was meant to swallow, shining clear and strong, far earlier than the curtain was ever supposed to lift. Something had already punched a hole in the fog, long before the old timeline said it could happen. And the galaxy behind that hole would become one of Webb's strangest finds yet. This galaxy is another one of those tongue-twisting catalogue names, so let us call it the Early Lantern, because it shone through the dark when it should not have. Webb saw the Early Lantern as it looked about 330 million years after the Big Bang. That is deep in the cosmic dark ages, when the hydrogen fog should still have been thick and grey across most of space. By the old timeline, this galaxy sat buried inside the mist, and yet, when scientists spread its light into a fingerprint, they found a strong, clear signal of glowing hydrogen. It comes from hot hydrogen gas around young, blazing stars. In the early universe, it is the one signal the fog was supposed to eat alive. The fog did not eat it. The glow came through loud and clear, like a lighthouse beam cutting straight through a storm that should have hidden it. That single result poked a hole in the old timeline. If the surrounding fog was still thick, that hydrogen glow would have been absorbed long before it reached us. The fact that we see it at all means something had already cleared the gas, at least near this galaxy, hundreds of millions of years earlier than the careful story allowed. Sit with how strange that is. The universe was supposed to stay foggy and sealed for a long stretch. The lights were supposed to come on slowly. Instead, here is a galaxy practically shouting through the mist at a time when the mist should have muffled everything. There are a couple of ways to explain it, and both are exciting. Maybe this galaxy was a fierce little furnace, blazing with so much hot, young starlight that it blasted the fog apart in a wide zone around itself. A small galaxy, but mighty, clearing its own window onto the universe far earlier than its neighbors. Or maybe whole patches of the early universe cleared up sooner than anyone thought. Maybe reionization, the great lifting of the fog, started earlier and ran faster in places than the old models predicted. Either way, the curtain was rising ahead of schedule. This matters far beyond one galaxy. Reionization is one of the biggest turning points in all of cosmic history. The moment the universe went from sealed and dark to open and clear. Scientists thought they had its timing roughly pinned down. The Early Lantern says the schedule needs a rewrite, and it fits the pattern we keep running into. Galaxies too bright, too soon. Heavy elements too rich, too soon. Now the fog clearing too early, too soon. Again and again, Webb shows an early universe that did its big jobs faster and more fiercely than the slow story expected. The young cosmos was busier than we ever pictured. Stars burned hotter. Galaxies grew quicker. The fog burned away ahead of time. A picture is forming, and it points toward a wild, violent, fast-moving dawn. But to clear that fog so early, a galaxy would have to do something dramatic to the space around it. It would have to carve out a bubble of clear space in the middle of the grey, and those bubbles turn out to be one of the most important features of the entire early universe. A young galaxy clearing the fog works a lot like switching on a lamp in a smoky room. The light does not clear the whole room at once. It carves out a glowing pocket of clear air right around the lamp, while the far corners stay hazy. Early galaxies did the same thing to the hydrogen fog. Each blazing galaxy poured out high-energy light that tore apart the gas nearest to it. Around every bright young galaxy, a clear bubble formed, a pocket of see-through space surrounded by a sea of grey fog. At first, these bubbles were small and scattered, like a handful of tiny clearings in a thick forest. But the galaxies kept burning, the bubbles kept growing, and where two bubbles touched, they merged into one larger clear zone. Over time, bubble joined bubble, until the clear patches spread and linked across the whole universe, and the fog finally vanished for good. That is the real story of reionization. The lights came on unevenly. The universe cleared up patch by patch, bubble by bubble, in a slow, uneven sweep that took hundreds of millions of years to finish. Now, here is why the early lantern matters so much. For its bright hydrogen glow to reach us, that galaxy must have already blown a big, clear bubble around itself, big enough that its light could escape the bubble before slamming into the surrounding fog. And it did this far earlier than the old story allowed. That tells scientists something powerful. The first galaxies were ferocious. To carve a bubble that early, a galaxy had to flood its neighborhood with intense light, the mark of furious star formation packed into a tiny space. These were blazing engines, strong enough to reshape the gas for thousands of light years around them. And it ties straight back to everything else. Webb has been screaming at us. A galaxy bright enough to punch an early hole in the fog is also a galaxy that is burning through stars at a reckless pace. The same fierce activity that makes these galaxies too bright and too chemically rich is exactly what let them clear the fog ahead of schedule. Every clue points to the same kind of place, a young universe full of intense, hard-working galaxies doing big things fast. So, the bubbles are more than a side detail. They are a fingerprint of how powerful the first galaxies really were. Each early clear bubble is a sign of a galaxy that was punching way above its weight, lighting up its corner of the cosmos long before it was supposed to. Picture the whole young universe from far away, a vast grey fog, slowly filling with growing pinpricks of clear light, each one carved by a furious little galaxy. The clear pockets spread and merge like holes burned through a sheet of paper until the grey is gone and the universe stands open and clear. Webb showed us those holes appearing too early. The galaxies that made them were too strong too soon. And that raises the next big question, the one hiding inside the brightness itself. Where does all that fierce light actually come from? Because scientists are starting to suspect that some of it is not starlight at all. Light is the only thing these distant galaxies send us. Everything we know about them, we squeeze out of that light. So when a galaxy looks far too bright for its age, scientists have to ask a careful question. What is actually making all that light? There are really only a few engines in the universe that can pump out that much glow. The first engine is ordinary stars, lots of them. A galaxy stuffed with bright, hot stars will blaze. We have walked through why that is a problem. To shine that brightly so early, a galaxy would need to build a giant pile of stars at a speed the old models can barely allow. Possible, maybe, if the first stars formed fast and furious, but it strains the rules. The second engine is stranger and far more powerful. A feeding black hole. In the center of a galaxy can sit a black hole millions of times heavier than our Sunday. By itself, a black hole gives off no light. But when gas falls toward it, that gas does not drop in quietly. It swirls into a flat, spinning disk first, like water circling a drain. As it spins, it crushes together and heats up to incredible temperatures, glowing white hot. A feeding black hole can outshine all the stars in its galaxy combined, throwing off the light of billions of suns from a region smaller than our solar system. So here is the trap for astronomers. From 13 billion light-years away, a galaxy crowded with stars and a galaxy with a blazing feeding black hole can look almost the same. Both are tiny points of intense light. Telling them apart is one of the hardest jobs in this whole hunt, and it changes the story completely. If an early galaxy is bright because it is jammed with stars, then the early universe built stellar mass at a shocking rate, and the timeline is in trouble. But if that same galaxy is bright because a black hole is feeding at its heart, then maybe it holds far fewer stars than it looks, and the mass problem softens. The brightness would be the roar of a single feeding black hole rather than the glow of a vast crowd of stars. That second idea would be a relief in one way and a nightmare in another. A relief because it could shrink some of the impossible early masses back toward normal. A nightmare because it would mean giant black holes existed at the dawn of time, and giant early black holes are their own enormous puzzle. This is why scientists hunt for clues to tell the two engines apart. A feeding black hole leaves marks. Its light flickers in ways starlight does not. Its spectrum shows wild, broad signals from gas whipping around the black hole at tremendous speed, and the light tends to come from one tiny central point rather than spread across a galaxy's body. When Webb started looking for those marks in the strangest early galaxies, it found something nobody expected. A whole population of small, intensely red, intensely compact objects scattered across the early universe. Tiny dots of fierce light that did not match a normal galaxy or a normal black hole. Scientists gave them a plain nickname, and that nickname now sits at the center of one of the biggest mysteries Webb has uncovered. They called them the little red dot. The little red dots are exactly what they sound like. Small, red, and almost perfectly round points of light, scattered all through the early universe. Webb found them by the hundreds, far more than anyone expected, and they have started an argument that still has not settled. At first glance, a little red dot looks like a tiny, faint galaxy, but its light tells a confusing story. Part of the glow looks like a feeding black hole with the fast, wild gas signals that giant black holes produce. Another part looks like old, settled starlight. The two clues seem to point in opposite directions at once, which is why scientists keep arguing about what these things really are. The leading idea is unsettling. Many scientists think the little red dots are powered mostly by black holes, feeding hard in the centers of small early galaxies. If that is right, it would explain a lot. It would tell us that some of the brightness fooling us in the early universe really does come from black holes instead of giant piles of stars. Some of the impossible early masses might shrink, but it trades one giant problem for another. To shine like that so early, these black holes would have to be huge, millions of times the mass of our sun, and they would have to exist when the universe was only a few 100 million years old. That is the new nightmare. Black holes are not supposed to get that big that fast. Think about how a black hole normally grows. It starts smaller and feeds on gas over time, packing on mass slowly because there is a speed limit on how fast it can eat. Feed a black hole too quickly, and the very light from the hot in falling gas pushes the rest of the gas away, choking off the meal. It is like trying to drink from a fire hose. Past a certain point, the force of it blows the food right back out of your mouth. By that speed limit, a black hole that started small after the Big Bang should still be modest a few 100 million years later. It should not be a giant yet. Yet the little red dots and other early galaxies hint at giant black holes sitting there far too soon. So scientists are stuck with a hard choice, and every option is strange. Maybe these black holes were born big, springing directly from the collapse of huge clouds of gas, instead of slowly building up from tiny seeds. Maybe they found a way to feed faster than the supposed speed limit, gorging in bursts. Or maybe the little red dots are something we have never seen before, a brand new kind of object from the early universe that breaks our neat categories. Whatever they are, the little red dots deliver the same blunt message as everything else Webb has found. The early universe built big things fast. Big galaxies, big black holes, rich chemistry, cleared fog, all of it, far ahead of the old schedule. And the brightness is only half of why these galaxies feel wrong. The other half is their size, because along with being too bright and too rich, these ancient galaxies are also strangely, impossibly small. And that smallness hides a clue of its own. Here is something that sounds backward. One of the most troubling things about these early galaxies is how small they are. Our Milky Way is a sprawling pinwheel. If you could fly across it at the speed of light, the trip would take about 100,000 years. It is a vast, loose city of stars, spread thin across an enormous space. The early galaxies Webb keeps finding are the opposite of sprawling. They are tiny and tightly packed. Some of the brightest ones cram a huge amount of light, and possibly a huge amount of stars, into a space only a few hundred or a few thousand light years across. Imagine taking a galaxy's worth of brilliance and squeezing it down into a fierce, dense knot, like packing a whole city's worth of people into a single stadium. That tight packing makes the brightness problem even worse. It is one thing to have a lot of stars. It is another thing to have a lot of stars jammed into a tiny volume, shining all at once from nearly the same spot. The light pouring off every patch of these galaxies is staggering, far higher than anything in the calm, spread-out universe we live in today. And density changes how a galaxy behaves. Pack stars and gas that tightly, and everything speeds up. Stars form faster because the gas is squeezed and dense. Stars die and explode close to one another, and their blasts slam into nearby gas, triggering even more starbirth. The whole place runs hot and fast, a pressure cooker compared to the leisurely galaxies of today. This fits the violent picture forming across our whole story. A galaxy this compact is a galaxy under intense pressure, building and burning at full speed. It would explain the fierce light, the early heavy elements, and the power to clear the fog, cram everything close together, and a small galaxy can act like a giant. But the smallness raises its own deep question. How did so much matter gather into such a tiny space so early? In the old, slow story, structure builds up gently over a long time. Gas drifts together. Galaxies grow loose and large through slow mergers. A dense, compact, fully lit galaxy at the dawn of time means matter rushed together far faster and far tighter than the gentle version allowed. Something had to pull all that gas into one small spot, hard and fast, right at the beginning. Gravity is the obvious suspect, but the gas and stars we can see may not have enough pull on their own to gather that quickly. That points to a hidden hand, an invisible kind of matter that we cannot see, yet that shapes everything in the universe with its gravity. Scientists have known about it for decades and still cannot say what it is. They call it dark matter. And dark matter may hold the key to how the early universe built its galaxies at such a breakneck pace. To explain galaxies this big, this bright, and this compact, this soon, the invisible scaffolding behind them would have had to assemble shockingly early, which leads to a question that reaches even deeper than stars and black holes. What if the real head start belonged to the part of the universe we cannot even see? Most of the universe is invisible. That is one of the strangest facts in all of science, and it sits at the center of this next puzzle. Everything you can see, every star, every planet, every galaxy, every person, is made of ordinary matter. Add it all up, and it accounts for only a small slice of the stuff in the universe. The rest is hidden. About 5 times more mass hides in something invisible, a kind of matter no telescope can photograph and no lab has ever made. Scientists call it dark matter. We know dark matter is there because of its gravity. It does not glow, so no telescope can photograph it directly, but it pulls. Galaxies spin faster than their visible stars can explain, as if extra invisible mass is holding them together. Across the cosmos, dark matter's gravity bends and shapes everything. It is the invisible skeleton the visible universe hangs upon. Here is how that skeleton built galaxies. In the early universe, dark matter started clumping together under its own gravity, long before ordinary gas could. It formed huge invisible blobs, which scientists call halos. Each halo is like a deep gravity well, an invisible bowl sitting in space. Ordinary gas then rolled downhill into those bowls. The gas piled up in the center of each dark matter halo, grew dense, and lit up as stars. So, galaxies are basically glowing pools of gas and stars, sitting at the bottom of invisible dark matter bowls. The halo came first. The visible galaxy formed inside it. Now, the timing question returns, sharper than ever. For Webb to be finding big, bright, compact galaxies at the dawn of time, the dark matter halos that hold them must have formed even earlier. The invisible bowls had to be ready first, deep and strong enough to gather gas in a hurry. The scaffolding had to go up before the building could rise. So, one possible answer to the whole mystery hides in the dark. Maybe dark matter gathered into deep halos faster than the standard story expected. Maybe those early halos were denser and more powerful, pulling gas together at a furious rate and giving the first galaxies the head start they seemed to have. If the invisible scaffolding rushed up early, the bright galaxies inside it could follow quickly. That idea is exciting and uncomfortable at the same time. It is exciting because it could explain why galaxies appear too soon, by pushing the real head start back onto dark matter. It is uncomfortable because we still do not know what dark matter actually is. Trying to fix one mystery by leaning on a second, deeper mystery is shaky ground, and there is a limit to how far this answer can stretch. If scientists have to bend the behavior of dark matter too hard to fit Webb's galaxies, they start tugging on the foundations of cosmology itself, the basic rules for how all structure in the universe grows. A small tweak is fine. A big one would mean the whole framework needs work. Step back now and look at the full collection of surprises. Bright galaxies, heavy chemistry, cleared fog, giant early black holes, compact, dense bodies, maybe rushed dark matter. Every clue points the same direction, toward a cosmic dawn that ran hot, fast, and early. So scientists are circling one bold idea. Maybe the gentle sunrise we imagined never happened at all. Maybe the universe began with a sudden, violent blaze. For decades, scientists pictured the birth of the cosmos as a slow sunrise, a soft, gradual brightening, tiny sparks here and there, slowly gathering, slowly warming, slowly building toward the grand universe we see today. Gentle, patient, calm. Webb has replaced that picture with something far wilder. The early universe now looks like a sudden ignition. Picture striking a match in a dark room and watching the flame leap to full size almost at once, instead of glowing softly for hours. The cosmos seems to have switched on hard and fast, blazing into life in its first few 100 million years. Every clue Webb gathered points the same way. Galaxies grew bright, shockingly early, as if star formation roared rather than crept. Heavy elements appeared far too soon, the sign of giant stars living fast and exploding quickly. The hydrogen fog burned away ahead of schedule, cleared by galaxies fierce enough to punch holes in the dark. Giant black holes may have been feeding when the universe was practically a newborn, and all of it was packed into tiny, dense galaxies running like pressure cookers. Put those clues together, and a single story emerges. The first few 100 million years were the most furious, fast-moving stretch in the history of the universe. The cosmic dawn arrived as a blaze, sudden and fierce. This is a real shift in how we understand the beginning of everything. The old idea was that better telescopes would simply fill in the same gentle story with sharper detail. Webb did something more disruptive. It showed that the story itself was off. The early universe worked faster, hotter, and harder than the careful models predicted. Now, this does not mean the Big Bang is wrong. The basic idea that the universe began hot and dense and has been expanding ever since still stands strong. What is in trouble is the fine print, the detailed rules for how quickly stars, galaxies, and structure were supposed to assemble. Webb has shown that those rules are missing something important about the speed of the early universe. Scientists put it in a blunt way. Webb handed them a stack of better, harder problems. The early galaxies are real, confirmed, and stubborn. Any model that wants to survive now has to explain how the cosmos built so much, so fast, so soon. And just when you might think the trouble ends at the edge of deep space, it reaches back toward us, into a question about the universe right here and now. Because Webb's surprises stretch beyond ancient galaxies. The telescope has also waded into one of the fiercest arguments in modern science, a fight over a single, simple number. How fast is the universe expanding today? It sounds like a question with an easy answer. Measure the expansion, write down the number, move on. But when scientists measure it two different ways, they get two different answers, and those answers refuse to agree, no matter how carefully anyone checks. That stubborn disagreement has a name, the Hubble tension, and Webb just made it worse. The universe is growing. Every galaxy, on average, drifts away from every other galaxy as space itself stretches. We met this idea earlier with the rising bread dough, the raisins spreading apart. Now we need to measure how fast that dough is rising. The speed of that stretching is one of the most important numbers in all of science. It tells us how old the universe is, how big it is, and where it is headed. Scientists have been trying to pin it down for nearly 100 years. To picture the problem, forget galaxies for a second and think about a balloon with dots drawn on it. As you blow up the balloon, every dot moves away from every other dot. A dot far across the balloon races away faster than a dot nearby because there is more stretching rubber between you and it. The whole surface is expanding, and the farther apart two dots are, the faster they separate. Space works the same way. The farther a galaxy sits from us, the faster it appears to rush away. Measure how distance and speed line up across many galaxies, and you can work out the rate of the stretch. That single rate is the number scientists are chasing. There are two main ways to measure it, and this is where the trouble begins. The first way looks at the nearby universe, the cosmos around us today. Scientists find special stars and exploding stars whose true brightness they understand very well. By comparing how bright these objects truly are with how bright they look from Earth, they work out exact distances. Then they measure how fast those galaxies are moving away. Distance plus speed gives them the expansion rate, measured close to home. The second way reaches all the way back to the beginning. Scientists study the faint afterglow of the Big Bang, a sea of ancient light spread across the whole sky, left over from when the universe was very young. Hidden in that ancient glow is a detailed map of how matter was arranged at the start. Feed that early map into our best understanding of physics, run the universe forward, and it predicts how fast space should be expanding today. So now we have two answers for the same thing. One measured directly from the nearby universe, one predicted from the early universe, run forward through the rules of physics. If our understanding were complete, the two answers should match perfectly. The near measurement and the far prediction should land on the same number. They do not match. The number from the nearby universe comes out higher. The number predicted from the early universe comes out lower. The gap between them is small but stubborn, and it has refused to close for years, no matter how much sharper the measurements get. That gap is the Hubble tension. Two careful roads to the same number, ending in two different places. Either one of our measurements is fooling us, or our understanding of the universe is missing a piece. And the more carefully scientists measure, the more the gap refuses to budge. What started as a small puzzle has grown into one of the deepest cracks in modern science. Because if the disagreement is real, it could mean something is wrong with our picture of the entire universe. A small disagreement between two numbers might not sound like a crisis, So why does this one keep famous scientists up at night? Because of what each road is built on. The near measurement and the far prediction are two of the most careful, most tested pieces of work in all of science. Thousands of people, decades of effort, and mountains of data stand behind each one. It is like two trusted clocks that have always agreed, suddenly showing different times. Either one of them is broken, or time itself is doing something strange. When two roads this solid arrive at different answers, you cannot just shrug and pick one. There are really only two ways out, and both are huge. The first way out is that someone made a mistake. Maybe the nearby measurement is slightly off. Maybe the early prediction is slightly off. A hidden error somewhere, a small flaw in how distances are judged or how the ancient light is read, could create a fake gap. If that is the answer, the universe is fine, and we just need to find the bug. The second way out is far more thrilling and far more frightening. Maybe both measurements are right. Maybe the near number and the far number are both correct, and the universe really did expand at one rate early on and a different rate later. If that is true, then our basic rulebook for the cosmos is missing something big. There is a piece of physics we have not discovered yet. Sit with that second option. It would mean the universe contains some force, some ingredient, some behavior we have never accounted for. Something that changed how fast space stretched between the early universe and now. Our textbooks would need a new chapter, maybe a whole new section. The most likely suspect, if new physics is to blame, is the strangest thing in the cosmos: dark energy. The mysterious push that makes the expansion of the universe speed up over time. We know almost nothing about what dark energy actually is, if it has changed in strength over the life of the universe. That alone could explain why the early and late measurements disagree. The expansion rate would have shifted because the push behind it shifted. So the Hubble tension is really a fork in the road for all of physics. Down one path, a measurement error gets found, the gap closes, and the universe stays simple. Down the other path, the gap is real, and we are forced to admit there is a hidden ingredient shaping the entire cosmos, one we have barely begun to understand. For years, most scientists hoped for the boring answer: an error, probably in the trickier of the two roads, the nearby measurement, which depends on carefully judging the distances to faraway stars. Those stars sit in crowded, distant galaxies, and their light can blur together with their neighbors. A little blur could throw off the distances, and bad distances could fake the whole gap. It was a reasonable hope. Clean up the blurry star measurements with a sharper telescope, the thinking went, and the troublesome gap might shrink to nothing. The crisis would dissolve into a simple correction. There was one telescope sharp enough to put that hope to the test. The same machine that had already shaken up the early universe now turned its perfect vision on the very stars at the heart of the argument. What Webb found pushed the crisis deeper instead of solving it. The doubt had a specific target. For the nearby measurement to be wrong, the problem most likely lived in a special kind of star that scientists use as a cosmic measuring stick. These stars have a rare and useful habit. They pulse, brightening and dimming over and over in a steady rhythm, and the speed of that rhythm reveals their true brightness. A star that pulses slowly is truly very bright. A star that pulses quickly is fainter. Once you know a star's true brightness, you can judge its distance by how dim it looks from here. The dimmer it appears, the farther away it must be. Scientists use these pulsing stars as the first rungs on a ladder of distance that stretches out into the universe. Get the pulsing stars right, and the whole ladder stands firm. Get them wrong, and every distance built on top of them tips over. Here was the worry. These pulsing stars sit in faraway galaxies, surrounded by countless other stars crowded close around them. Through older telescopes, the light of a pulsing star could blur together with its neighbors. A blurry blob might look brighter than the single star really is. and a star that looks too bright would be judged too close. That kind of mistake, repeated across many stars, could throw off the whole distance ladder and fake the entire Hubble tension. So this was the clean, hopeful escape. Blame the blur, fix the crowded star measurements, and the gap might close. Then Webb looked. Webb's vision is sharp enough to pick out individual pulsing stars cleanly, even in crowded, distant galaxies, separating each one from its neighbors in a way older telescopes could not. It was like swapping a smeared, foggy photo for one in crisp, perfect focus. If crowding and blur had been faking the brightness, Webb's clean view would reveal it. The stars would shift, the distances would correct, and the gap would shrink. That is not what happened. When Webb measured those pulsing stars with its sharper eyes, the old distances mostly held up. The nearby measurement did not collapse. The crowding worry, the great hope for a simple fix, turned out to be a much smaller problem than people wished. The high nearby expansion rate stood its ground. This was a quiet bombshell. By checking the weakest link in the nearby measurement and finding it solid, Webb closed off the easiest escape route. The disagreement could no longer be waved away as a blurry star problem. The local number was real, and it was still higher than the early universe predicted. Consider what that means. Scientists had two suspects for the Hubble tension: a measurement mistake or new physics. Webb just made the measurement mistake much harder to blame, at least on the nearby side. And every time you rule out the boring answer, the thrilling and frightening answer grows more likely. The telescope built to study the dawn of time had wandered into a second great mystery and made it sharper, exactly as it had done with the early galaxies. Webb keeps doing the same thing wherever it looks. It removes the easy excuses and leaves scientists staring at a real problem. By the year 2026, with the easy fixes fading, scientists took a hard look at where all the numbers actually stood, and the gap was still sitting there, stubborn as ever. By the year 2026, scientists had thrown everything they had at the Hubble tension. New telescopes, new methods, fresh measurements using different kinds of stars, different exploding stars, and entirely separate techniques that do not lean on the same ladder at all. If the high nearby number were a fluke caused by one bad method, all these independent roads should have wandered off in different directions, and the disagreement would have dissolved into noise. Instead, the opposite happened. Method after method, using different tools and different assumptions, kept landing near the same high value for the nearby expansion rate. That is the part that makes scientists nervous. It is one thing for a single measurement to disagree with a prediction. It is another thing entirely for many separate measurements to all agree with each other and still disagree with the prediction. The nearby universe keeps insisting on one answer. The early universe keeps insisting on another. Let us put rough numbers on it, just to feel the gap. The measurements tied to the nearby universe keep pointing to an expansion rate in the low to middle 70s. In the units scientists use, the prediction drawn from the early universe lands a few notches lower, closer to the high 60s. The two camps are separated by only a handful of units. That sounds tiny. It is anything but tiny. The wiggle room on each measurement has shrunk so much that this small gap now sits far outside the range either side can explain by chance. Both numbers are measured tightly. Both refuse to move toward the other. A small space separates them, and that small space has become a canyon that physics cannot cross. A summary backed by NASA in the year 2026 laid it out plainly. The nearby measurements still point high. The early universe prediction still points lower, and the careful work of the last few years, much of it sharpened by Webb, has made both numbers more trustworthy than before. The disagreement stands on firmer ground than ever, so the dream of a quiet solution has mostly faded. For years, the hope was that better data would gently pull the two numbers together. The opposite occurred. Better data drove the two numbers apart with more confidence, locking each one more firmly in place. This is why the Hubble tension has grown from a curious puzzle into one of the biggest open questions in physics. It will not go away. It will not shrink. The harder scientists look, the more real it becomes. just like the impossible early galaxies at the edge of the universe. And the two mysteries may be whispering to each other. The same telescope sharpened both. The early universe is acting strange, building galaxies too fast. The expansion of the universe is acting strange, refusing to agree with itself. Some scientists wonder whether one hidden idea, one missing piece of physics, could be behind both surprises at once. But before we reach for a grand new theory, honesty demands one more hard question. We have ruled out a lot of simple mistakes. Could there still be one quiet error hiding in plain sight that makes this whole crisis disappear? Because the history of science is full of revolutions that turned out to be plain mistakes, and good scientists always check the unglamorous answer first. Science is full of monsters that turned out to be mistakes. A signal that looked like faster than light particles once turned out to be a loose cable. A famous hint of ripples from the early universe melted away when scientists realized they were seeing ordinary dust. So when Webb hands us a pile of impossible galaxies and a stubborn expansion gap, the responsible first move is to ask whether we are fooling ourselves. Let us be fair to that idea, because parts of it might be right. On the early galaxy side, some of the shock has already softened, and more of it might. A few galaxies that looked as heavy as the Milky Way shrank once scientists measured them with care. Some of the blinding brightness probably comes from feeding black holes rather than vast crowds of stars, which would lower the star counts. Better data keeps trimming the wildest claims. It is possible that smarter models of fast star formation, violent stellar winds, and early black holes could absorb most of the surprise without breaking anything. On the expansion side, the door is not fully shut either. The early universe prediction leans on our understanding of the leftover glow from the Big Bang and on assumptions about what the cosmos is made of. A subtle, shared error in those assumptions could, in theory, still be hiding. Scientists keep hunting for it, so the boring answer is genuinely on the table. Maybe both crises are a mix of small errors and incomplete models, and the standard story survives with patches and tweaks. But here is why scientists cannot relax. The surprises keep surviving the cleanup. Every time a strange early galaxy gets measured more carefully, it loses some of its extremes, and yet the basic problem remains. Trim the masses, and the galaxies are still too bright and too early. Blame the black holes, and now you have giant black holes existing far too soon, which is its own crisis. The trouble refuses to fully drain away. Squeeze it in one place, and it bulges out in another. The expansion gap behaves the same way. Each new method that should have closed it instead confirmed it. Each easy escape that scientists checked turned out to be a dead end. A single error can fool one measurement. It strains belief that the same error secretly fooled a dozen different ones, all in the same direction. This is the difference between a fluke and a pattern. A fluke shows up once and fades. A pattern shows up again and again, in different places, measured by different people with different tools, and it refuses to fade. Webb keeps turning flukes into patterns, and a pattern is hard to wave away with one clever fix. So the honest verdict in the year 2026 sits in the middle. We have not proven that physics is broken. We have also failed, again and again, to make these problems disappear. The simple errors keep getting ruled out, and the surprises keep standing. That is exactly why the headline on all of this is so carefully worded. What Webb found at the edge of the universe is troubling for our theories and thrilling for science, all at the same time. To understand why, we need to look closely at what those two little words really mean. Not good. And why, for scientists, that phrase is a strange kind of gift. Headlines love the word broken. Webb broke the universe. Webb broke physics. Webb broke the Big Bang. The truth is calmer and, in a way, more interesting. The Big Bang is fine. The core idea, that the universe began hot and dense and has been expanding ever since, rests on a mountain of evidence that Webb has not touched. Nobody serious is throwing that out. The leftover glow from the early universe is still there. The expansion is still real. The broad shape of cosmic history still holds. What Webb stressed is the fine print, the detailed rulebook for how fast the early universe was supposed to build stars, galaxies, structure, and chemistry, and the detailed rulebook for how the expansion should behave from beginning to end. Those detailed rules are the parts showing cracks. The big story stands. The fine details are in trouble. So the better word is incomplete. Our model of the universe works beautifully for most of what we see, yet it is missing something important about the earliest, fastest, most extreme moments. A map can be mostly accurate and still be wrong about one wild stretch of territory. Webb has found that wild stretch. This is why scientists do not panic. They get excited. For a researcher, a confirmed problem is the most valuable thing in the world. A theory that explains everything perfectly leaves nothing left to discover. A theory with a real, stubborn crack is a doorway. It points straight at something new, waiting to be understood. That is the strange gift hidden in the phrase "not good." It is not good for the simplest, tidiest version of cosmology, the version that expected the early universe to be calm and slow and the expansion to be perfectly predictable. That comfortable version is the thing in trouble. For science itself, this is a golden age. Webb has handed researchers a generation of deep, juicy problems to chase. Think of how the biggest leaps in history actually happened. They almost always started with a measurement that refused to fit, a small anomaly that would not go away. Scientists chased the anomaly, and it cracked open a whole new understanding of nature. The orbit of one planet that drifted slightly wrong led to a brand new theory of gravity. A few stubborn problems can rewrite everything. Webb has handed us anomalies on a silver platter. Galaxies too bright and too early. Chemistry too rich too soon. Fog cleared ahead of schedule. Giant black holes that should not exist yet. An expansion rate that disagrees with itself. These are the kind of cracks that, in past centuries, led straight to revolutions. So when you hear that what Webb found is not good, hold both halves of the truth at once. It is genuinely bad news for the simple, gentle picture of the cosmos that scientists carried for decades. That picture is wobbling, and it may not survive in its current form. And it is wonderful news for everyone who wants the universe to still be full of mysteries worth solving. The universe just told us that we do not understand its beginning as well as we thought. That is humbling. It is also the most exciting thing a curious mind could hope to hear. What scientists do with all these cracks is the next chapter of the story. And there are a few very different paths forward, each one leading to a different version of reality. Faced with all these impossible early galaxies, scientists have sketched out 3 main escape routes, 3 different ways the universe might have pulled off its fast, fierce dawn. Each one is being chased right now, and each one rewrites a different piece of the story. The first route is the gentlest. Maybe these galaxies are simply lighter than they first appeared. The earliest brightness measurements were rough, and rough numbers run high. As scientists pin down the masses with careful spectroscopy, some galaxies that looked as heavy as the Milky Way shrink to something more reasonable. If most of them shrink enough, the crisis softens. The galaxies would still be surprisingly early and bright, just no longer flatly impossible. This route saves the most of the old story. It asks only that we stop overcounting. The second route is darker. Maybe much of the early brightness comes from feeding black holes rather than huge crowds of stars. We met this idea with the little red dots. If a black hole is roaring at the center of an early galaxy, it can fake the light of billions of stars while the galaxy itself holds far fewer. That would slash the star counts and ease the mass problem in one stroke. The catch is steep. It trades a galaxy crisis for a black hole crisis, because giant black holes at the dawn of time are just as hard to explain. The trouble moves onto the black holes instead of vanishing. The third route is the boldest. Maybe stars really did form far faster in the first few 100 million years than any of our models allowed. Maybe the early universe was a star factory running at full blast, building stellar mass at a pace we simply did not think was possible. If true, the galaxies are exactly as massive and bright as they look. The fix would live in our understanding of how stars are born. The measurements would stand as they are. This route keeps the galaxies real and rewrites the physics of star formation. Notice something about all three. Even the gentlest route still demands change. None of them lets the old, slow story walk away untouched. The smallest fix asks us to accept that the early universe was more efficient than we believed. The biggest fix asks us to rewrite how the first stars and galaxies were built. Somewhere between those two, the answer is waiting. And the real answer is probably a blend. Some galaxies are likely lighter than they first looked. Some are likely powered partly by black holes. And the early universe probably did form stars faster than the old models assumed. Reality rarely picks a single clean explanation. It usually mixes several together. To figure out the recipe, scientists need more of exactly what made the problem clear in the first place. More confirmed distances, more detailed fingerprints from more early galaxies, better ways to tell a galaxy full of stars from a galaxy hiding a feeding black hole, and much smarter computer simulations that try to grow a universe from the Big Bang and see whether it can build galaxies as fast as Webb keeps finding them. Each of these three routes leads somewhere different, but they all sit inside one bigger choice, the deepest fork of all. And the direction science takes from here depends entirely on which way that final fork bends. Everything in this story comes down to one final fork in the road. It is the biggest question in cosmology today, and scientists honestly do not know which way it bends. The first path is the calmer one. Maybe all of Webb's surprises can be absorbed by fixing our astrophysics, the rules for how stars, galaxies, and black holes behave. Better models of fast star birth, smarter accounting for feeding black holes, a clearer picture of how the first galaxies blazed and cleared the fog. If that work is enough, then the big framework of the universe survives. We patch the details, the impossible galaxies become merely surprising, and the Big Bang model lives on, wiser and stronger. A major repair, but no revolution. The second path is the earthquake. Maybe the surprises cannot be patched. Maybe no amount of clever modeling can explain galaxies this big, this bright, and this early, alongside an expansion rate that refuses to agree with itself. If that is the case, the trouble reaches all the way down to the foundation. We would need new physics, new ingredients in the early universe, perhaps a different behavior for dark matter, or a changing dark energy, or something nobody has even imagined yet. Down that second path, the universe we thought we understood becomes a stranger place. The rules we trusted would turn out to be a special case, true near home, but breaking down at the dawn of time. That would be the kind of shift that reshapes textbooks for a century. So which path is it? The honest answer, right now, is that nobody knows, and that uncertainty is the living edge of science, happening in real time, with the answer still unwritten. Here is what makes this moment so rare. You are alive while it unfolds. The galaxies in Webb's images are billions of years old, but the questions they raise are brand new. Every few months, the telescope confirms another impossible galaxy, sharpens another measurement, rules out another easy answer. Scientists are arguing, testing, and rebuilding their models with the data still pouring in. The story of the early universe is being rewritten right now, and none of us knows the ending. Step back and feel the full size of what Webb has done. We built a golden eye, chilled it near the cold of deep space, and flung it 1,000,000 miles into the dark. We pointed it at the faintest, oldest light in existence. And that light came back carrying a message we did not expect. The universe was bolder at its birth than we ever dreamed. It built faster, burned hotter, and grew up quicker than our finest theories allowed. That message is humbling. After all our cleverness, the cosmos still managed to surprise us at the deepest level in the story of its own beginning. And it is thrilling because a universe that can still surprise us is a universe with secrets left to find. Webb handed scientists a stack of beautiful, stubborn problems instead of a finished answer, the kind that turn a great telescope into a historic one, and a quiet field of science into a revolution. The edge of the universe is calling, and we have only just begun to read what it wrote. That is where we will leave it, staring into the oldest light there is, knowing the next discovery could change everything we think we know.